Right, welcome back. We're going to cover, this week we're going to cover soil chemistry, and we're going to do that in two sessions rather than do everything in one. And right now we're going to look at soil pH and cation exchange capacity. So the concepts here, we're going to look at soil pH and why it's important, and why we care, both in terms of plant nutrients and growth, and then also to some extent environmentally. And then the second notion that I want to cover is this whole notion of cation exchange capacity. What kind of cations are we looking at? You know, why do we care? And then also look at the concept of base saturation. In our next talk, we'll have a look at soil fertility, but that's all part of this week's covering of soil chemistry. Love this picture. I'm not sure what that guy's spraying. I hope it's not something poisonous, because if I had the camera, I'd want to have something on me as I go along, but it's a great picture. Okay, soil scientists often call pH soil reaction. And what you can see is that it's just a measure of the acidity or the alkalinity of the soil. I'm sure you've seen this 100 times before, this particular chart here. So baking soda being quite basic and vinegar being quite acidic. And an additional look at this is looking at some of the soils that you might find across the globe. The sodic and the calcareous soils are going to be found typically in more dry environments, whereas your acid sulfate soils are obviously your forested soils you're going to find in wet environments, especially where there's a tremendous amount of weathering. You're going to find that kind of level. So the take home here is not only do we have variations in pH, but there's no one single pH that's perfect for soils in general. You're going to find soils in natural situations where pHs vary. Your types of acidity, you know, most of the time we just talk about our active acidity, and that's basically the amount of hydrogen ions in solution. It's a very, very small quantity. Not much calcium carbonate would be required to neutralize natural acidity in soils. So typically, you know, you're looking at about 4 pounds of lime per acre to neutralize maybe, you know, the soil, say, from a pH of 6 to a pH of 7, somewhere around that. So that's typically what you'd apply on soils in terms of a liming application. The exchangeable and reserve or residual acidities, there's a much higher quantity, but they're not readily seen in the soil. But the readily exchangeable hydrogen and aluminum ions in the soil complex are, there's a lot more than the active acidity that you see, and fortunately we don't see that in most natural soils. There's a lot of reserve or residual acidity. If you had to break that soil down even more, you have a lot more acidity there. But in this discussion, really what we're going to talk is about active acidity. And we have to ask, well, why do we care about soil pH? Well, it's an incredibly important element, and we care about it in terms of, number one, how it affects nutrient uptake in various plants, and we'll cover that later on. Number two, there are some plants that are specifically adapted to acidic or basic environments. And then acidity also affects soil microbiology or soil biology, and it's going to affect biological populations as they go along. Let's have a look at plants first. You'll find that sweet soils, which have pHs of from neutral down to about 6 or so, you'll find that there are certain plants that favor the sweeter soils and are less tolerant of the acidic soils. And then you move across the spectrum, and things like blueberries, azaleas, and rhododendrons much prefer more acidic soils. Now, I would comment that grasses will grow in those sweeter soils, but typically this is what you're going to find in systems. These are the soil pHs a lot of these plants are going to favor. So one wants to take into account the species of plant one grows in a natural soil environment. So not an artificial one where maybe it's been in some kind of annual for a long time. Interestingly, is hydrangeas. You can actually modify your hydrangea to have pink flowers or blue flowers, and some people sort of treat one side of the plant, say with a little bit of ammonium sulfate or something, to actually lower the pH, so you can get this color difference in the flower. So that's just kind of an interesting thing that you find. So pH is also known as the potency of hydrogen, little p and then big H, and it's the standard method of the acid-base equilibrium, and your pH is always the negative log to the base 10 of the concentration of your hydrogen ion. So a pH of 1 is going to be very, very acidic. A pH of 14 will be extremely basic. So neither of them is particularly conducive to soils, but for example, these are some calculations that you can use. I'm not going to run through them, but I'm probably going to do some of these in class, so bring your pencils and papers with you on that. But those are basic calculations. You can use Microsoft Excel as well to help you in that process. So what are the sources of acidity in soils? Well, one of the biggest sources of acidity in today's soils is this process of nitrification. When we apply commercial fertilizers, we apply them in the form of ammonia, NH4, or ammonium ions, NH4. They hit the ground and they are immediately set upon by microbes, nitrifying microbes, bacteria, that then combine the nitrogen with oxygen to form nitrates, water, and then here we've got 2 hydrogen ions. Those 2 hydrogen ions then go free, essentially, and usually displace either calcium or magnesium or sodium in the soil matrix. And they will then push those ions off, and the calcium and magnesium then begin to leach out. And when that happens, you begin this process of acidification. To a lesser extent, in a natural system, organic matter decomposition will also generate hydrogen ions. But again, in natural systems, this all takes place over a much longer period of time, whereas you can go ahead and put 120, 130 pounds per acre of ammonia on the ground, and you find this takes place in a much shorter time. So yes, it happens, but in a natural system, you've got all sorts of checks and balances for this to happen. In soil respiration, carbon dioxide and water combine to form carbonic acid or bicarbonates. So this is the carbonic acid and this is bicarbonates. They will be in equilibrium with one another, and they will be then in the soil pore spaces in the water, and so you would find slightly acidic concentrations there. When plants uptake basic cations, so the basic cations are going to be calcium, magnesium, potassium, and then to a certain extent sodium. When those are taken up, basically the OHs are released, and the they no longer contribute to the OH in the soil solution. Hydrogen ions are released into the soil solution and essentially make that soil more acidic. And often these two processes are interrelated. Those basic cations are then leached out, and that leaching process then leaves the hydrogen ions basically sitting in the soil, and you're going to have that acidic soil. So remember that soil acidification by and large is a natural process. Remember eudic soils or eudalts in the southeast are going to be naturally slightly more acidic as a matter or as a functioning of the weathering. But we aid the acidification process a little bit through things like land clearing of native vegetation. Production agriculture contributes to it mainly because of the addition of commercial nitrogen in the form of ammonium. And it can become a plant growth stress factor. So you can see these are roots, I don't know which plant, but at a pH of 6.5 they look very good. pHs of much lower, you can see that you're going to have some problems over there. When pHs get really low, we find that aluminum gets solubilized in the soil and it becomes toxic to plants. We see this in some states, it's more apparent in some states than other. I believe Vermont is a state that is very aware of that. In agricultural operations, the acidification of the soil is combated by lime addition. It's a fairly simple process, and we'll look at that. I would add a caveat over here, is that all of this soil chemistry that we have takes place in an environment or assumes very, very little interaction with the soil biology. Once we introduce soil biology, the dynamic changes, but from a soil pedologist's point of view, often the notion of soil biology and the very active participation of soil biology in the chemistry is fairly low, especially in these agricultural fields. Therefore, these premises hold in kind of artificial agricultural fields where you've got lots and lots of annual crops and you're not dealing specifically with the effects of the soil biology, i.e. your organic matter contents is very low. When we look at cation exchange capacity, we're looking at the amount of exchangeable cations that a soil. Now remember, the clays and the organic particles are the ones that are negatively charged. So these are the ones that are really being able to absorb those ions. And the cations that we have, basically you'll have a soil particle with those negative charges, and it's going to attract those cations: calcium, magnesium, potassium, those are all, and sodium. Those are all your basic cations, and then you'll also have, it'll attract hydrogens and aluminum if they're around. So it's the amount of these cations that the soil can attract. Some soils attract them better than others. There's actually something called anion exchange capacity in some of the soils. We have the oxasols. Remember, those are the highly weathered soils that you'll find in the tropics. Very warm, very wet. And basically, in this case, a lot of the soils are positively charged. And they will actually attract anions, and as you see there. In our part of the world, that's not an issue. So I just wanted to mention it to you. We're going to go back to cation exchange. With cation exchange, you have this equilibrium going on, where your clays in equilibrium with you've got hydrogen ions in the soil, and then your a given cation, and there will be a certain amount of equilibrium. If you increase the amount of hydrogen ions in the soil through acidification, what you're going to do is you're going to drive the reaction this way, and your calcium is going to end up in solution. If you have less hydrogen ions in the soil, your calcium is going to kind of stick more, and you're going to drive the reaction this way. Your cation types, we've discussed your basic cations: calcium, magnesium, potassium, and sodium. Your acidic cations are going to be that aluminum, the 3+ aluminum 3+ cation, and the hydrogen cation. You really want to, you like these guys over here. You don't necessarily want to have those guys around. Okay, so cation exchange is influenced by certain things. The first is the strength of absorption. In the previous slide, you saw the strength of absorption between the basic and the acidic anions. Over here, you're looking at aluminum's strength of absorption is the highest, and so it's going to replace a calcium or magnesium if it's around in solution, and these guys are tied to that clay. Hydrogen then is your lowest strength of absorption, but if there's enough hydrogen ions around in that soil solution, it's going to kick those others out. Notice that the ammonium ion is part of that, so if your nitrogen or if your ammonium ion is not actually nitrified, it actually will stick onto your soil as an ammonium ion. Once it's turned to a nitrate, it has a negative charge, and it's repelled by those soil particles, and that's why it leaches. The other thing, well, we just talked about it, the relative concentration of the above cations in solution. So even the strength, even though hydrogen ion strength of absorption is very low, you put enough hydrogen ions in the soil, and they will kick some of these basic cations off the soil. These guys will leach out into the soil solution. You don't want that to happen. So that brings us to the calculation for cation exchange capacity. Really the take home over here is that it comes in what we know as milliequivalents per milligram or centimoles per kilogram. But if you have a look at say something like Clemson, it always comes in MEQ. So let me write that down. It's going to be MEQ per milligram. But basically, cation exchange capacity is calculated in terms of moles, and it takes valence into account. So you would have an amount of the element, say calcium. You would then, if you had to flush it off a soil, you would then divide it not only by the your molecular weight, you'd actually multiply it by the valence as well. In this case, calcium has a valence of 2, magnesium has a valence of 2. So I don't want to get too hung up in it, but for instance, you add all of the ability or of the cation exchange capacity up, which would give you a certain amount of cation exchange capacity. And your base saturation would be the sum of all your basic cations. In this case, those 4, calcium, magnesium, potassium, and sodium. Multiply that by 100 and divide it by the cation exchange capacity. So going, because your cation exchange capacity is 13, and your hydrogen, the amount of sites that are occupied by your hydrogen is 3 centimoles per kilogram, or milliequivalents. Your percentage base saturation would be 10 divided by 13, which would be 77%. So we've covered soil chemistry, soil pH, soil chemistry in the form of soil pH and cation exchange capacity. We'll go on to have a look at another aspect of soil chemistry, which is the whole notion of soil fertility. Keep in mind, soil fertility is also then linked back to the whole idea of soil pH and very much cation exchange capacity. So hopefully this has been helpful, and you have one more lesson, at least one more talk in this week to go. See you in a bit.
Lonely, 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 lonely time.